Hi, guys. Welcome to week 4 of remote learning. Today's date is Wednesday, April 22nd, 2020. Okay, we're going to go ahead and continue on with our Unit 7 stoichiometry. Again, as always, for your notes, you're going to go ahead and need a pen or pencil to write this stuff down, paper, unless you're choosing to do it on a Word doc, and your calculator so you can plug some numbers in. Yeah, so as I said, we're still on Unit 7 stoichiometry, but our focus has shifted. Okay, last week we were focusing primarily on limiting reagents and excess reagents. This week, the focus is on percent yield and percent error, okay? So we're still dealing with stoichiometric calculations. We're still going to be dealing with limiting reagents. Now we're just adding one more layer, okay, of calculations. Percent yield and percent error, basically what that deals with is if you take any reaction, doesn't matter what it is you're doing, if you look at any reaction, it's never going to go, usually anyway, it never goes to 100% completion. And so what that means is if I stick gas into my car and I turn on my car and I go for a drive, we know that the engine in my car, assuming you don't drive an electric vehicle, that's a combustion reaction. The fuel is reacting with the oxygen in the air, and your products are carbon dioxide and water, right? So we assume that all of the gasoline gets used up in our cars. It reacts with oxygen, and we have a perfect combustion reaction. Generally, that's not the way the world works, guys. We never really have perfect reactions. So some of that gasoline might not be used up completely. Some of it might get lost. Some of it might get left behind in the engine. We might just not burn any of it. And so what this deals with, okay, what percent yield and percent error deals with is in a perfect situation, I'm going to be burning 100% of my gas. I'm going to be using 100% of my chemicals. Okay. In reality, I might only use up maybe 80%. Okay. So we're going to be doing calculations that get us to a point that lets us know how much of our product are we making. Okay. Because we're not always going to make 100% of our product. We're not always going to make a perfect cake. Okay. Things happen along the way and we end up with less of a cake, less of a product than what we normally would have in a perfect world. So I get this is a lot of talking. I'll go ahead and shut up now so we can look at some actual examples. So hopefully it'll make a little bit more sense. Okay, as always, I love to start off with an analogy because I want to make sure that we move into this seamlessly. So I'm taking last week's example of the grilled cheese. Okay, so just like last week, okay, BD stands for bread, CH stands for cheese, BD2CH, that's our formula for a sandwich. Okay, here's our recipe for a sandwich or our chemical equation for a sandwich. We need 2 slices of bread for every slice of cheese to make one sandwich. All right. Now, here's our first example. And this is just going to be, again, this is part of the analogy to get you guys thinking about what we're doing here. Notice part of this is the same example that I used last week when introducing limiting and excess reagents. It's just been slightly modified a little bit to fit what we're trying to do this week, okay? So the example says, suppose you have 10 slices of bread and 7 slices of cheese. After trying to make a sandwich for the first time, you're only able to make 3.5 sandwiches. So it's your first time ever attempting to make a sandwich. Unfortunately, all you can make is 3.5 sandwiches from what you're given, okay? So the 2 questions that are being posed in this example are, what is the actual yield of sandwiches made, okay? What did we actually end up making? And what is the theoretical yield of sandwiches we can make, okay? In theory, in a perfect world, okay, how many sandwiches can we make? So I'm just going to go ahead and include our formula here for making a sandwich. For every 2 slices of bread we have 1 slice of cheese. 2 slices of bread, 1 slice of cheese gives us 1 sandwich, okay? So again, this is our chemical equation for making a bread, or our recipe for making a bread. 2 slices of cheese, or I'm sorry, 2 slices of bread to every slice of cheese gives us 1 sandwich, okay? Now, the problem above gives us 10 slices of bread and 7 sandwiches. So we're given 10 slices of bread and 7 slices of cheese, not sandwiches, okay? All right, so we need to go ahead and figure out our limiting reagent in this case. How many sandwiches are we able to make here, okay? So the first thing we need to do is start with what we're given, okay? So the first thing we're going to do is figure out how many sandwiches we can make with 10 slices of bread, all right? So remember, I did this last week, so I'm just going to kind of zoom through this real quick. So we have 10 slices of bread, okay? Now for every 2 slices of bread, we have 1 sandwich, right? Now, slices of bread cancels, and we're left with sandwiches. So we are left with 10 BD2CH divided by 2. That gives us 5 sandwiches, okay? Now we're going to go ahead and do the same thing with our 7 slices of cheese, just as we had last week. So we have 7 slices of cheese. We're going to pop that over 1. Okay, and now for every single slice of cheese, we make 1 sandwich. Okay, again, cheese cancels, leaving us with sandwiches. And we multiply across and we divide. We end up with 7 BD2CH divided by 1. That gives us 7 sandwiches. Okay, so last week, I just want to go over these numbers again. Remember, I said last week, this right here, 5 sandwiches, is all we can make, okay? Because once we've made 5 sandwiches, we've used up all of our bread, okay? Which means that we can't make 7 sandwiches because we don't have enough bread to make 7 sandwiches. So this guy right here, our 5 sandwiches, is the most that we can make, which means, okay, that bread is our limiting reagent. I'm going to put LR for limiting reagent. And our 7 slices of cheese, this is our excess reagent, ER. Now that we've established that 5 sandwiches is all we can make, okay, this is where we go ahead and start talking about actual yield and theoretical yield, okay? In theory, in a perfect world, we can make 5 sandwiches, okay, given the ingredients that we have. So if we were to use up all 10 slices of our bread perfectly, we didn't drop any on the floor, the dog didn't run in here and jump on the counter and take a couple slices, your little brother, little sister didn't come in and snatch a slice. If we used all 10 slices without anything happening to them, perfect situation, we can make 5 sandwiches, okay? Now, this right here, guys, this is our theoretical yield, okay? This is our perfect world scenario. Okay, in a perfect world, you are going to make yourself 5 grilled cheese, okay? Now, that isn't always the case, and in fact, you don't end up making 5 grilled cheeses in this case. As the example states, you are only able to make 3.5 sandwiches, okay? So let's go ahead. I'm just going to go ahead and clear this up real quick so I can continue talking about the difference between the two. Okay, as I said, in a perfect world, our theoretical yield gave us 5 sandwiches. Okay? Now, you don't make 5 sandwiches, okay? Something happens along the way and you're only able to make 3.5 sandwiches, okay? So, we've answered question B. We kind of skipped over question A. What is the theoretical yield of sandwiches we can make? Okay, in theory, we can make 5 sandwiches. Now, part A asks, what is the actual yield of sandwiches made? Guys, that's 3.5 sandwiches, okay? So, in reality, our actual yield, that gave us 3.5 sandwiches. Okay, now this usually happens, guys. Really, most of the time, we're not able to make. Ooh, did not mean to move that. We're not able to actually make a perfect amount of product. Okay, you're dealing with super small particles, guys. You're dealing with things we can't see with the naked eye, right? So chances are you're going to lose something that's extremely small, right? If we go back to our copper lab, when we started with copper, put it through a series of reactions and ended up with copper, no one ended up with 100% of their copper at the end. I had a few of you who fudged your numbers and made it seem like you did, and I called you out on it right off the bat. It just really doesn't happen too much, guys. Most of the time, you're going to have a yield that's different from what you can make in theory, all right? Okay, so now let's go ahead and get into the next portion of this example here. Okay, so now, we know that the actual yield of sandwiches made was 3.5. That's unfortunately how many you were able to make. Now, theoretically, in a perfect world, we could have made 5. You could have made 5 sandwiches, but that didn't turn out to be the case, okay? So we want to know, A, what is the percent yield of sandwiches made? And B, what is the percent error? So let's go ahead and get into those calculations real quick then. So the first thing we're going to do is figure out part A, percent yield. Okay. Now the formula for percent yield is our actual yield divided by our theoretical yield times 100%. Okay. This is your formula for percent yield. So let's go ahead and plug this in then to figure out what our percent yield was. Okay, so in actuality, we were only able to make 3.5 sandwiches, right? Theoretically, with all the bread, with the 10 slices of bread that we had, we could have made 5 sandwiches. Now, 3.5 divided by 5 times 100%, when you plug that in, that gives you a value of 70%. So our percent yield was 70%. Given the amount of ingredients that we had, we were only able to usefully put 70% of the ingredients to use. 70% of our reactants were used efficiently, okay? That means we wasted about 30%. We lost about 30%. In a lab situation, this number isn't terrible, but you certainly want to aim for 80% or higher. Okay, next thing we're going to go ahead and aim for is our percent error. Okay, so the percent error is going to equal the absolute value, okay, of our theoretical yield minus our actual yield divided by our theoretical yield, okay, times 100%. So this is the value, or excuse me, this is the formula for our percent error. Okay, so let's go ahead and plug this in then. Percent error is going to equal our theoretical yield, which was 5 sandwiches, minus our actual yield, which again was our 3.5 sandwiches. Oops. Absolute value of that, divided by our theoretical yield again. Okay, times 100%. And when you plug that into a calculator, you should end up with a value of, oh, look at that, 30%. Wow. Okay. So another formula for percent error is actually, let me just go ahead and erase this. Okay, I'm assuming you've copied this down. Another formula that you can use for percent error is going to be 100% minus our percent yield. You can use either one to solve for percent error. So make sure you guys copy down these two formulas, or at least one of these two formulas, preferably this top one if you're only going to copy down one, but I would encourage you to get down both as well. Okay, so let's go ahead and get into some definitions here. So the theoretical yield is the quantity of product calculated to form when all of a limiting reactant is consumed. Or in other words, another way of putting it, this is basically the maximum amount of product you can obtain. And this is completely dependent on the amount of limiting reactant you have. Okay, so as for the actual yield, okay, the actual yield is the amount of product that you actually obtained. Okay, so the theoretical yield is what you can make in theory. What's the most amount of product I can make based on the amount of limiting reactant I have? Okay, the actual yield is what you actually end up with, because sometimes your limiting reactant doesn't get completely used up, or it doesn't actually all go towards the reaction. Okay, so when that happens, you end up with the actual amount, which is almost always different from the theoretical amount. Okay, so the actual yield, the amount of product actually obtained, I'm just going to go ahead and add this onto this right here. So the amount of product actually obtained is almost always less than and can never be greater than the theoretical yield. Okay, so here's our first real-world example. All right, so when benzene reacts with bromine, bromobenzene is obtained. Okay, so this is a two-part question similar to our analogy. Okay, here what we have is for part A, when 30 grams of benzene, I'm just going to underline the benzene, reacts with 65 grams of bromine, all right, what is the theoretical amount of bromobenzene? Okay, so let's not move on to part B just yet. Let's just make our focus part A, okay? And then in the next slide, we'll go ahead and focus on part B. So for part A, okay, we want to know what's the theoretical amount of bromobenzene that we can form. Okay, in theory, how much bromobenzene can we form when we use 30 grams of benzene and 65 grams of bromine? Okay, so this is a limiting reactant question, guys. We want to know between these two reactants, which one is going to limit how much we can make, because that, in theory, is going to be the most amount of bromobenzene we can form. So let's go ahead and start off with our benzene. Okay, so for our benzene, we have 30 grams. Okay, 30 grams of benzene. All right. Now, we need to go from grams of benzene to moles of benzene. Okay. So in order to do that calculation, we actually need the molar mass of benzene. And I actually have that right here. So our molar mass of benzene is 78.1134 grams per mole. Okay. So 30 grams. All right, we have 78.1134 grams per 1 mole of bromobenzene. As we know, we multiply across and then we divide. Grams cancels, leaving us with moles as well. And what we end up with is 30 moles of bromobenzene divided by 78.1134. Okay. Now what that gives us is 0.38 moles or mole of bromobenzene. Okay. So we figured out how many moles of benzene we have. Now what we want to do is figure out, let me just go ahead and write this real quick. We know how many moles of benzene we have. Now we want to know how many moles of bromobenzene we have. Okay, so to do that, we just need to go ahead and use the formula, right? We need to use the coefficients in our chemical equation to figure out how to do that. So what we're given, what we know we have is 0.38 moles of benzene. Okay. Now, what we're given, one second, let me just go ahead and shrink this up a little bit, guys. Just need to make a little bit more space for myself. So what we have here, let's go ahead and take a look at the formula, okay? So for every single mole, for every 1 mole of benzene we have, we form 1 mole of bromobenzene. Okay, so we're going to go ahead and write that in. We have 1 mole of benzene to every 1 mole of bromobenzene. Okay, again, we multiply across and then divide. And when we do that, we end up with 0.38 moles of bromobenzene. Okay, so that was just for our benzene. Now we need to go ahead and do the same thing for our bromine. Okay, so I'm going to go ahead and erase this, and then we'll go ahead and start off with our bromine. Okay, same thing, guys. We have grams of bromine. First thing we need to do is figure out how many moles of bromine we have. Okay, so we have 65 grams of bromine. All right, the molar mass in this case is going to be 159.808 grams. Grams cancels, leaving us with moles. And we end up with 65 moles divided by 159.808. And that gives us 0.41 mole of bromine. Okay, so now from here, just like last time, we need to go from moles of bromine to moles of bromobenzene. Okay, so we have 0.41 moles of bromine. We set this up. For every 1 mole of bromine, we have 1 mole of bromobenzene. So it's just like what we did for our benzene. I know there's a lot of bromos and zenes being thrown in here in these sentences. 1 mole of bromine to 1 mole of bromobenzene. Oops, I keep writing that line there. Okay, and what we end up with is moles of bromobenzene, which is going to be 0.41 moles of bromobenzene. Okay, so just so we have everything here on the same board, I'm just going to rewrite what we got. So we ended up with 0.38 moles of bromobenzene. And this is what benzene gave us, right? Now our bromine gave us 0.41 mole of bromobenzene. Okay, so here we have these two different values. Okay, we have these two different values. Okay, now let's go ahead and determine what the limiting reagent is in this case. Okay, now 0.38 moles is obviously less than 0.41 moles. And so what this tells us is that our benzene, our C6H6, is what's going to limit the amount of bromobenzene we can make. In other words, once we use up these 30 grams of benzene, this is the most product we can form. So in other words, this right here, okay, this right here is our theoretical yield. Okay, and our benzene, okay, is our limiting reagent. Okay, so our theoretical yield is tied to our limiting reagent. Okay, our limiting reagent is going to determine what the most amount of product is that we can form. Okay, in this case, once we've used up, or when we use up, I should say, all 30 grams of benzene, in theory, we can make 0.38 moles of bromobenzene. Okay, this is the max amount of bromobenzene we can form using, or once our limiting reagent has been used up. Now, the next question asks, okay, our next question here asks, okay, I'm on part B now. If the actual yield of bromobenzene is 42.3 grams, what is the percent yield? Okay, so let's go ahead and figure that out. Okay, guys, so we can do one of two things here to figure out what our percent yield is going to be, okay? We can go ahead and take our theoretical yield of bromobenzene and convert it from moles of bromobenzene to grams of bromobenzene, or we can take our actual yield of bromobenzene and convert it into moles, okay? It doesn't matter what you do. You can go either way. What I'm going to go ahead and do is I'm going to go ahead and convert our moles of bromobenzene into grams of, oops, see, there I did it again, into grams of bromobenzene, okay? And I have the calculation right here. So 0.38 moles of, or mole, excuse me, mole of bromobenzene, okay? We take into account the molar mass. The molar mass of bromobenzene is going to be 156.95 grams per 1 mole. And what happens here, as you know, moles cancels, leaving us with grams, and we end up with a value of 60 grams of bromobenzene. Okay, so this is our theoretical yield This is our theoretical yield in grams. That's all we just did, okay? So now we have the value of our theoretical yield in grams and the value of our actual yield in grams, okay? So let me go ahead and clear this board up, and then we'll do the final calculation. All right, so remember that our formula for percent yield is going to equal our actual yield divided by our theoretical yield times 100%, right? So just like when we made that sandwich, okay, we were only able to make 3.5 sandwiches. That was our actual yield. We should have, in theory, been able to make 5 sandwiches, right? And we ended up with a percent yield of 70%. In this case, numbers are a little bit different. Okay, what our percent yield is going to be here, or I'm sorry, what our actual yield is going to be here is 42.3 grams, okay? And our theoretical yield was 60 grams, okay? So we have 42.3 grams divided by 60 grams times 100%, all right? And what that gives us is a value of 70.5%. What do you know? It's pretty close to our sandwich percent yield, okay? So that's our percent yield, okay? And actually, you know what? I forgot to throw in part C of this question. Let's go ahead and figure out what our percent error is, okay? So we can take 100% and subtract this value from it, or we can do it the long way. I'm going to do it the long way just to show you guys that equation one more time, okay? So we have our theoretical minus our actual, the absolute value of that, divided by our theoretical times 100%. So what that is, again, our theoretical was 60 minus our actual, which is 42.3, divided by our theoretical times 100%, okay? And that gives us a value of 29.5%, okay? So here you have it, guys. Our percent yield, okay, and our percent error. These are the two equations we went ahead and went over. I know it's kind of there's always a lot of background to each of these new concepts, but seeing as how it's your first time dealing with this sort of thing, that's why I make these videos as long as they are. You know, feel free to skip to whatever part you need to. I'm sure some of you are even skipping through some of the videos because you already, you know, kind of have an idea of what's going on. That's perfectly fine. Anyhow, if you come across any problems, you have any questions or concerns, of course, you can always email me or text me or call me. But that's it for this week, guys.